And I'm here together with Christopher, who will quickly introduce himself.
The competition. And then we have one more colleague.
Christoph, and I'm a scientist at CERN, working on the Atlas experiment and mainly doing physics analysis.
Okay.
Hello.
So to give you a quick overview of what we are going to do, for the next 20 minutes or so, Christoph is going to give you an introduction into the physics of CERN. Then Sarah is going to tell you details about the organization of Beamline for Schools. And then I'm going to tell you more about the technical details of the competition. And at the end of each block, we are going to take your questions. But now let's start with Christoph.
Could you please be louder? We are not being able to hear you.
Oh,
Say again?
they cannot hear us.
Could you please be a bit louder? We here at India, we are not being able to hear you properly.
Okay.
Doesn't matter where you're from.
Wait.
Hold on for a
Is this
second.
better now?
Marcus.
Yeah, thank you.
Yeah, it's
Is it okay? Okay. But so Christoph, you have to speak close to the microphone.
Marcus, really quickly, can I say something?
Yes,
This is
please.
Bob from TED.
Hello.
Hey. Hello, everyone. I just wanted to get on really quickly. Sorry that I'm late. One thing about the call, that I wanted to say is that for the sake of keeping everyone silent, because there are over almost 40 people on this call, for the sake of creating order, I'm going to mute everyone but Marcus.
Good.
What I would appreciate is if I mute you, I need you to please stay muted. So please don't unmute your mic until Marcus asks you to do so. If you do unmute your mic, what will happen is it can cause feedback. It can cause for us to hear a lot of noise. That'll distract you, but also that will make the call harder to understand. So for the best way for this call to work, I need everyone to stay muted. I also need everyone to not speak until the very end when Marcus asks for everyone to do so. Okay? So I'm gonna go ahead and mute everyone. And like I said, if you don't unmute yourself.
And one question to Ted. Can you see the slides that we are sharing?
Yes. I can see that with everyone. Can.
And the call will be recorded as well, right?
Yes. Yep. I've pressed record, so the video is now recording.
Okay, great.
Good. On the slide that you see at the moment, you have the location of Geneva on the left-hand side. The red square there shows the location of CERN.
Because we are still not being able to hear you that clearly. Could you be a bit louder?
Okay.
I can clearly hear you.
Yeah. So I'm sorry. Unfortunately, if you're not able to hear, that means that that's something wrong with your connection, not the video.
Okay. Fine.
Yeah, no worries. So I'm sorry. If there's anything that you can do on your side to raise the volume, try and do that. But
Your voice is quite audible. I think it's Marcus' voice which is slightly okay, fine. Your voice is now audible to us. Yeah, thank you.
Okay, good. Well, I'm trying to speak as loud as possible. I hope you can understand me.
Yeah, this is better. This is good. Thank you.
Okay. Yeah, I was saying that on the screen you now see on the left side the location of CERN on the map of Geneva. As we are going to explain you later, at the moment all the accelerators at CERN are switched off for maintenance. That is why in this year and in next year, in 2020, the Beamline for Schools experiments actually take place in a different laboratory. It is DESY in Hamburg. So on the right side, you see the location of Hamburg in the north of Germany. And in the center, you see where we are located in Central Europe. So this is just to give you geographic context. But now we continue with the introduction into the physics by Christoph Schmid.
Thanks a lot, Markus. So I'm going to tell you a little bit about CERN, what CERN provides for the experiments, and then tell you also a little bit about the experiments that are carried out here. So CERN is the largest laboratory for particle physics in the world at the moment. There's an annual budget of about 1.2 billion US dollars, or take any currency more or less. Then we have about 2,600 staff working at CERN, 900 fellows and students, and about 11,000 guest scientists, which are in one or another way associated to one of the experiments carried out at CERN. And in addition to the annual budget of CERN itself, as the laboratory comes all the external funding for the experiments, because those are not covered by CERN. On the map, on the left-hand side, you see the 22 member states of CERN, and this basically covers all of Europe. The ESI is the largest physics lab within Germany. It has a comparatively small budget, but still substantial means to carry out scientific research. The staff is similar. It's about 2,300 staff working there, 700 students and postdocs, and about 3,000 guest scientists. Again, plus external funding via universities, and they carry out experiments with synchrotron light, so high energy photons.
Hello.
And are also involved in neutrino physics. So our common goal is the fundamental research, the exploration of the structure of matter. So to give you an order or an idea of the size of the scales that we're talking about here, if one takes a crystal in the order of tens of millimeters, this was studied already in the 4th to 5th century. Then molecules in the order of 10 to the minus 9 meter are a lot smaller. Then we go to atoms, 10 to the minus 10 meter, and the nucleus inside 10 to the minus 40 meter. This was studied beginning of the 20th century. And then starting from the 60s, people took care about how they can model the inside of a single proton or a neutron, which is composed out of quarks and gluons, which keep the quarks together. And this is actually the active field of research that we do at the LHC Energies, is exactly the study of the constituents of the nucleons. How do we do this? Well, we need a lot of accelerators, as you probably know. So we use electric fields to accelerate particles, at CERN usually protons. And this is a simple schematic how you do this. You just take 2 electrons, you put a proton in between, and the protons are accelerated by the electric field. You want to reach higher energies, you do this multiple times, one after the other. So this is a schematic of a linear accelerator. Between these little tubes, you always apply a high voltage, so the protons are accelerated in the electric field in between. And while they are inside the tube, you can change the polarity of the field so that between the next 2 tubes, they again see an accelerating field. And by doing this, you can reach medium energies of several mega electron volts. So the same as putting the proton or another charged particles through a voltage difference of a few million volts. If you want to go to even higher energies, you have to build circular accelerators or very long linear accelerators. At CERN, we use a lot of circular accelerators. They are always built like seen in this schematic on the current slide. So you have to use accelerating structures, which you see at the top and the bottom, to give the particles more energy. Then bending magnets, you see in gray, that keep the particles on the circular trajectory. And focusing magnets, you see in blue, to keep a nice narrow beam size. And then a few additional parts to inject and extract the beam if you want to. These accelerators are not only used at CERN, they can also serve different purposes. For instance, in medicine, they can be used to treat tumors, in so-called hadron therapy, or also heavy ion therapy. So we have a small accelerator, you accelerate the particles and you shoot them basically in tissue to destroy tissue at a well-defined place. And around the world, a few of these centers have been built in the recent years, one, for instance, in Heidelberg in Germany. At CERN, you find quite a lot of accelerators. This gives you a map of the accelerators we use. So the protons start in LINAC 2. It's this purple line with LINAC 2 written, and then goes through a whole lot of circular accelerators, the booster, the proton synchrotron, the super proton synchrotron, and eventually reaches the LHC, which is the big circle at the top. And from nearly every accelerator on, you see lines splitting off, which feed the protons to different experiments. So at CERN, we do much more than just the LHC experiments. In fact, we have over 40 different experiments carried out at CERN, all related to particle physics. From
Hello.
the top? From the top?
Can anyone hear me?
Yes, we can. We come to asking questions in a second. So from the top, you see this overview of Lake Geneva on the right-hand side, the Jura Mountains on the left-hand side, and in between you see the few of the accelerators indicated, the LHC, which is the large circle, the SPS, and the proton synchrotron. And the circumference of the LHC is 27 kilometers, and it's about 100 meters below the surface. So physics-wise, what we do is, or what we know about physics is all part of the so-called standard model. You see on the left-hand side the particles that we know of. The upper violet boxes indicate the quarks that we know. These are the constituents, the protons and the neutrons. Below in green, you see the leptons and the neutrinos. Leptons, for instance, contain the electrons and muons. This is probably well-known leptons. In red, we see the gauge bosons. Those are the particles that transmit the forces. And then in yellow, you see the Higgs boson. It's the newest addition to the family, which was discovered in 2012 at the LHC. For every particle, there's also an antiparticle. And this basically includes all the particles we know. And all the laws of particle physics dictate how these particles interact. And this is what is studied in great precision at the LHC. The forces we know is the strong force, which binds together the quarks in the nucleon, the electromagnetic force, which dominates our daily life completely, and the weak force, which is responsible for radioactive decay. We also know gravity, but we don't really understand it, so this is not part of what we call the standard model.
Hello, sir. Could you hear me? Hello, sir.
Yes, we can, but we ask questions in a little bit. If you can wait that long, that would be great. Thank you. So this model does not answer all the questions. It does not answer the question why there is no more antimatter in the universe, or what the origin of dark matter is. Neither does it explain how gravity works. And because there are these and many more big unknown questions is why we carry out these experiments here. What happens in these experiments is when we shoot protons at each other, they have the highest energy we can reach in the accelerator, and they produce a whole lot of secondary particles. You see a schematic in the figure on the right-hand side, where in every collision we have about order of hundreds of particles coming out and being detected in these huge detectors. In early years of CERN, around the 60s, it was done a little bit different way. So we had bubble chambers where you could really see the trajectory of charged tracks on photographs. On the left-hand side, you see a picture of these photographs. So the incident particles from the beam come from the bottom of the picture, and then you see an interaction point, and the curved particles are charged particles which are bent in the magnetic field, and you also see some particles decaying. And by looking at these pictures, you can reconstruct what happened there. And there were about 100 million of these photographs taken in 25 years at CERN, and a lot of people, in fact typically women, looked at these pictures, classified them, and essentially did the analysis of what you could see in the picture. Today we do it a little bit different, so all the detectors are read out electronically via computers, and we get out these nice events displays you see here. This is an example from the Atlas experiment, where we have several simultaneous proton-proton collisions, which you see in the little inset in the picture on the top. And what we are most interested in is these high energetic tracks marked in red that go out through the detector, traverse, in this case, all of the detector, though these are 4 muons and is a candidate for a Higgs event. And only one Higgs event is expected for every 1 billion, for every 1,000 billion collisions. So what do we do with all this data? So I want to show you a few relatively recent scientific results. Of course, after the discovery of the Higgs boson in 2012, we want to study its properties. So just discovering it is by no means enough. We really want to understand how it interacts with the other particles. And this is shown on this graph. You see the particle mass with which the Higgs interacts on the x-axis, and on the y-axis, you see the coupling strength. So how likely it is that the Higgs boson interacts with this particle. And you see this measured for muons, for taus or leptons, also for quarks, for the B quark, and for gauge bosons for the W and the Z, as well as for the top quarks in the very right corner. And they all are on the expected line, which is the blue dashed line expected from the standard model of physics. This is an enormous result showing the consistency of this model. But then we, of course, want to also search for new particles. However, none have been seen so far. Also, this is a very important information to theorists, that we didn't see any new things in the available phase space, in the available energies and topologies. And then we also do a lot of precision measurements of interactions of the standard model particles that I just showed you before. And this is an overview of this. You see different reactions on the x-axis, a whole lot of different reactions. And on the y-axis, you see the cross-section of these reactions. So the measurement, how likely it is that a particular reaction occurs. And you can see that we measure this over 14 orders of magnitude. And in gray, you always see the theory predictions, and the blue markings are the experimental results at different energies and datasets. And they are all in a very good agreement, nearly all. And this is a fantastic achievement to measure something like this over 14 order of magnitudes. So it shows that the standard model is very consistent, very precise, and that we have really still no good clue about these big questions that I showed you just before. And the last slide, I just want to show you that we also do some a bit unconventional studies at the LHC. For instance, this year at the Atlas experiment, again, we discovered, or we observed for the first time directly the scattering of 2 photons of each other. This is a process that in classical electrodynamics, this is forbidden, that 2 photons interact with each other, but at very high energies, and using quantum mechanics, you can predict that this might happen, and indeed we see that it happens. And this is a result which is a bit off the standard analysis with a small team, and also this can be done at these big experiments. And I think now's time for the first question and answer session.
Okay. Well, let me add that if you did not understand all the physics details, don't worry, I didn't understand them either, because I'm not a physicist, I'm an engineer, and you don't have to understand physics at these depths in order to enter the Beamline for Schools competition. But we just wanted to show you the spectrum of the research that's being done at CERN. So we are not yet talking about BL4S, we are talking about physics and the research. And now is your time to ask questions to Christoph about these research topics. After this Q&A session, he's probably going to leave us.
Yes.
And we are then continuing more specifically on Beamline for Schools. Okay, so your questions about physics now.
Hello.
Yes, go ahead.
Hello.
All right. So I'm.
All right, hold on. Sorry. I want to try and do this in a little bit of an orderly way, because it's
Okay.
not going to work if everyone starts to ask questions at the same time. So what I'm going to say is, unfortunately, if you're on the phone, you'll probably be unable to ask questions. I deeply apologize. If you are joining us through video, what I'm going to ask is that you chat your group name into the chat box. Once I see your group name, I will call upon your group, and then that will give you a signal to ask your question. If we all start talking, it's going to be mayhem. So it's going to be really hard to ask or to answer any questions. So once again, if you see the chat box in your right hand, you can type in your name or your TED club name, and from there I will call on you or allow you to start asking questions. Does that make sense for everyone? Marcus, does that work for you?
That's fine, yeah.
Okay, great. Let's start with the Contemporary Education Academy, and then after that, we'll go to TED DPS Noida. Hold on for 1 second. Okay. I think they muted themselves. I didn't mute them. The TED Ed, there we are. Is the Contemporary Education Academy on? If so, you can unmute yourselves. I'm not muting you anymore.
Yes.
Okay, so
Hi.
Uh,
We already know.
yeah, we
You
remember
do.
you.
Yes, we've met before. What's
Hi.
your
So we have a couple of questions, and
Yeah.
not Ali will start.
Hi. So my question is that are your experiments eco-friendly and environmentally friendly?
So at the moment, I would classify them not as environmentally friendly, but we're working on getting the whole lab more environmentally friendly. As you can imagine, the experiments, some of them at least, use a lot of energy so a lot of electricity, and there's not much we can do about that. However, we do reduce or even ban environmentally damaging gases, for instance, which has been used in cooling and stuff before. This is not done anymore. And for the lab itself, we did a lot of effort in the last years to be more eco-friendly in the sense that very basic things, for instance, that trash is separated, that we use reusable cup in the cafeterias. You can imagine we have thousands of people every day in the cafeterias, so we have in a year easily millions of cups, which used to be thrown away. This is not happening anymore, so we are actively working on it becoming more eco-friendly.
Okay, so I have another question. So what do you think makes this organization experiment superior? What's the biggest advantage of it?
So what the advantage of this lab in particular is that it's very much international. So we have people from all over the world working here, bringing different experiences. And this is extremely beneficial for the lab. And this is a very unique organization also from this point of view in the world. Because we don't only have labs from Europe, we also have labs not only from Europe and North America, but really the whole world that participate in these experiments. I think this is the main thing that is unique. And then, of course, concerning the scientific research possibilities, this is the highest energy accelerator in the world that we have. So these experiments carried out, and that accelerators are not possible at any other place at the current time.
Wow.
Okay, thank you.
You mentioned people working on the projects, they're international, but I would like to know how are gender roles distributed in your workplace? So how many women are working there?
There actually was a recent study about this, and I think I don't know the numbers from the top of my head. Does anybody of you know by chance?
Yeah, I think it's about 25 to 30% females in physics.
Yeah.
In physics, maybe.
Yes.
Totally, and at CERN, it's about 20% women at CERN currently.
This is due to the fact that we have a lot of engineers hired by CERN.
Sorry, Contemporary Education Academy. We're gonna move on to another group to have a chance to ask a question. I'm so sorry, and thank you all, and it was good to see you all again.
Stay connected.
Stay connected. We're going to move on to Kartiki from TED DPS Noida. So let me see, Kartiki.
Hello.
Hello, are you there?
This is Karthikeya.
Hey,
Hello.
Kartiki, how you doing?
I'm fine. I'm from India. Hello from India, from Delhi.
Hello.
Hello. So what is your question?
Yeah, so I would like to ask for a more physics-based question actually. So, all right. So first question, I've got two questions actually. So I'll ask them one by one in succession. So first of all, you talked about the particles that you actually do, the particles that you collide together in the, I think the Large Hadron Collider, right? So my question to you is, what is the actual element that you use in order to find those particles and actually obtain those particles so that you uh, use them in your experiments?
So the particles we collide is protons, really. We collide protons and we obtain them from hydrogen. So we literally take a bottle of hydrogen gas and we ionize it, and then we just have the electrons and the protons, and they can be very easily separated in an electric field, and then we get a beam of protons.
All right. And another question of mine is that, all right. So, what I have heard about the Higgs boson is that I've heard it being called the God particle. Now the problem is that even though I'm just a school student, so I don't really understand the physics of the Higgs boson, right? So if you could tell us in layman's language, what does it actually mean, and why is it actually known as a God particle?
So I personally don't like the term God particle, I have to say. I can briefly tell you where this comes from. So this comes from a book. There was a director of CERN, of Fermilab. Director of Fermilab wrote a book about the hunt for the search for this particular particle, which was very elusive for more than 40 years. So it was very hard to find. And he wanted to write the goddamn particle. And his lecturer said, you can't write this, but you can write the God particle. It's much better selling. So this is how that name originated. It got nothing to do with a godlike figure or so. So what the Higgs particle does, the Higgs particle is important for the standard model of physics that I talked to you that describes what we know about particle physics, in the sense that it couples, so it interacts with all particles that do have a mass. And it allows new processes, and these processes take care that in all reactions probability is conserved. We call this that the model is unitary. So probability conservation means that the chance that a reaction happens can never be larger than 1. And without this in the model, we find theoretically these reactions. So this is one thing. And the other thing that you always hear probably, and you probably know, is that it's connected to the origin of mass. So we assume, or as we understand that fundamental particles acquire mass, is that it's a dynamic process and it happens through the interaction with the Higgs field. So through that interaction, mediated through the Higgs boson, particles can acquire mass. This is something not straightforward to grasp, but this is also very important in the theory.
Okay.
Thanks a lot.
Next one.
Thanks a lot.
Let me see. The next group will be. Oh, there's my. Okay. So this is what I'm gonna say. One, I think we probably won't have a lot of time to get to everyone's questions. In case we don't get to everyone's questions, what you can do is if you drop your question in the chat, I can ask them. Also, what can happen is after this call, I can send them over to the team so that potentially the team can send them back with answers if that works for you, Marcus.
Well, there is a very nice question now. I read it out. It says, what could cause the end of your work? Hypothetically, what could make you scientists stop? I think we will only stop when we stop being curious. As long as we are curious, we keep researching. And I think our curiosity is infinite. Well, the second thing that could stop us is that we completely understand the universe.
Unlikely to happen anytime soon.
Exactly, that's unlikely to happen anytime soon. There are still many, many questions open about the universe. And well, we also have to be honest with you. The third thing that could stop us doing science is that we lose the funding for it.
Yes, that's more likely to happen. How is all this statistical information collected by the experiments? Well, so we do these collisions of protons very, very fast. So this happens 40 million times per second. And then we have to select which of these collisions are interesting for us. And in the end, we store about 1,000 of them per experiment per second to disk. So they are just stored to hard drive. And then later, over the course of many months or even years, this is analyzed, all that information. In a typical analysis, we analyze some billions of events.
Mm-hmm. The next one is, can we find a unified theory of physics? Well, that means finding a theory that would merge quantum physics with relativity. This is something that physicists have tried for the last 80 years without success so far. So if you have a theory to propose, well, go ahead, you're going to get a Nobel Prize.
So we're working on this. I mean, this is still actively very much worked on, but it's probably not going to be anytime soon.
So then the next question was how information is analyzed. Well, briefly, with a lot of computers and a lot of software that we are developing for that purpose.
And it's analyzed all over the world, not just at CERN.
Oh, yeah.
So then somebody is asking about the current research of antimatter.
Oh, I'm not the expert there, but there is a dedicated facility to do this.
Yes, we have a facility to produce antimatter. We can produce anti-electrons, we can produce antiprotons, and we can bring them together to form antihydrogen. What we are looking at the moment is whether antimatter behaves the same way as matter in a gravitational field. So more easily formulated, does antimatter fall down or does it fall up? We are looking at the color of antimatter. We are looking at the weight of antiparticles. The next question is about the upgrade of LHC. No, I don't think that we are going to see much about.
So there was a question about the upgrades, and no, we will probably not see anything about string theory. What the upgrade does is they increase the rate of collisions.
Mm-hmm. Okay. Well, it's difficult to follow the influx of questions. Yeah, but as soon as there's a new... Hold it. Okay. Any parties covered during our experiments this year?
This year, so Atlas didn't discover a new particle. LHCb, I believe, did two new mesons.
Mm-hmm.
So 2 new particles.
Yeah. We did not have anything that was as spectacular as the discovery of the Higgs particle.
Sir, could you hear me?
Let me go back to the next question. So there was a question, I'm not sure if you're answering all of them. Would it be possible to contain a few micrograms of antimatter? Well, we can contain antimatter, we can store it for more than a year, but microgram is much too large a mass. We are collecting a few hundred atoms, which is, well, 10 to the minus 26 kilograms, something like that. The amount of antimatter that we are producing is very small, but we can store it for a very long time.
Oh yeah, so this classification, why women classify this, this is a tribute to the time of the 60s. So this were typically the
I'm sorry to interrupt. I'm sorry to
partners of
interrupt. May I say something?
No, please wait. What kind of experiments are you doing there? Here at CERN, we are doing experiments to research into the fundamental laws of nature in the microcosm. We're trying to understand the smallest particles, the smallest constituents of nature.
Or invent something. So there's a question depending on what the experiments you make, are you willing to create or invent something exact? Do you have that main article you were thinking about? So I guess this refers to if we have an application of the research result in mind, and no, we don't. So what we do is really fundamental science. We don't have any products or any applications for this in mind. It's really just for the research.
So I think let's just pick out a few questions. There is one, do you see the relationship between religion and science? I think that is a question that every one of us has to answer on a personal basis.
Absolutely.
But I believe something that has helped us as a community is to separate two questions. We separate the why from the how.
Yeah.
Here in physics and science, we are looking at how things work. How does a proton collide? How does a Higgs particle decay? And we leave to the religious domain why these things happen. So there is a question about dark matter, Christoph?
So have we learned anything about dark matter? Yes, we learned a lot because we now know a lot of places where there is, so a lot of, let's say, mass ranges or phase space, as we call it, where there is no dark matter. So we have excluded a lot of possibilities for dark matter. We did not find any evidence, any direct evidence for dark matter so far.
There is one very important question. It's the last one. I read it out. Please answer our questions since school is going to get shut. That's important. So I think we should now stop this more general session and thank Christoph. If we have time, we can come back to it. But we should now give you the essentials about the Beamline for Schools competition. So I'm going back to sharing the slides. And then Sarah will talk you through the BL4S.
Sir, sorry to interrupt. I can't hear you. Can you be more audible?
Well, we are trying to speak as loud as possible.
Enjoy the rest of the session. Bye-bye.
Bye-bye. No, da fehlt was.
Ja, da können wir später drauf zurückgehen.
Okay, good. Okay, so we start now with some basics about the Beamline for Schools competition. I think that's the most important thing why you all connected today. So you see some nice pictures of last year's winning students here. So the idea really of this competition is that students will become actual scientists and really work like scientists so that they get an insight of what this is really like, which can also help
No,
you.
sorry to interrupt. Can you be more? I can't hear you. Can you be more audible? Please, I can't hear you.
But I don't think, honestly, that's the problem we can solve. It might be your connection because I think everyone else can hear us. I can talk a little bit louder, but there's not much more I can do. Okay, so the best way is really to get your own experience, because seeing it on television or something is one thing, but really doing it yourself is a totally other thing. And many students said it helped them a lot to get insights really into what it is like to be a scientist. So the idea behind this competition is really that it's competition for high school students, really from students from all around the world. We often get the question, can I take part, although I'm from this country, whatever. But everyone can really take part. You don't have to be situated in a country which is a member state of CERN or anything. Everyone really can take part. So what you have to do is basically you have to phrase a scientific question and get an idea of an experiment you would like to do which uses a particle beam. This idea you have to work out a little bit more and send us a written proposal of up to 1,000 words and also a 1-minute video where you explain a little bit what you want to do, present your team and so on. And of course there's much more information and examples of this on our website as well. So you can of course get help from your teachers, from professors at universities, from other mentors wherever they might be. But the main thing is that the students really work out the idea and that they really understand what they want to do, because you are the ones, you students, who we will actually invite and who will do the experiments together with our scientists. So how do we select then finally the winning team? So we have a big scientific committee with usually about 60 volunteer scientists from CERN and DESI mostly, and we actually evaluate these proposals concerning, first of all, of course, the feasibility. So if we cannot conduct the experiment, of course, that would be a pity. And when we finally find the winning teams, evaluating motivation and the feasibility and the experiment itself, we invite, as Markus already pointed out, the 2 winning teams also next year to the laboratory DESI in Germany, and there we will meet them and conduct these proposed experiments then together with you, the winning teams, whoever it might be next year. So, and when the competition is over, the program is over, it's not really over for the students, so we are still in contact with the winning teams from the last years, and you can write up your results and even publish a scientific paper before you go to university or have another career, which is quite unique. Very important date is the deadline, so it's always end of March. 31st March next year. Until then, you will have to submit your proposal, the written proposal, and the 1-minute video in order to take part in this competition. So, and now we go more into the technical part, that you understand a bit what is available, and this Markus will give an insight into.
Yeah. Well, I'm going to give you a very brief overview of the instrumentation that you can use in order to build your experiment. All the information and much more is on our Beamline for Schools website in a large document that tells you everything about the beam conditions and the instruments. So this is really just to give you a little bit of an idea. When you're doing an experiment in particle physics, you have to realize that as humans with our senses, we cannot detect these particles, we cannot see them, we cannot hear them. Therefore, we have to use special detectors, and for that purpose we have detectors that are called scintillators. They give us small electric signals when they are interacting with a particle. We have so-called calorimeters. They tell us about the energy of a particle. And then we have detectors that we are using for tracking. Tracking means that we record the position at which a particle has been seen. These tracking detectors are so-called delay wire chambers or micromegas or beam telescopes. And we also have one detector which is called, complicated name, a multi-gap resistive plate chamber, which is to measure the time that a particle needs to move from position A to position B. So by combining these,
so could you just repeat what you said right now? Like,
yes,
so there was some interruption.
By combining these particles, by combining these detectors, you can find out about the particles that are seen by your experiment. You can find their properties, and you can then draw some physics conclusions from the data. We also have a data acquisition system. This is based on software that we have developed here at CERN, and we can record the information of up to 5,000 particles per second. But that's a technical detail. Well, don't get carried away with that. We also have some magnets that can be used to bend the trajectory of a particle. This is very useful if you want to, for example, measure the momentum of a particle. But you will see when you read the document how exactly this all fits together. What you have to take away from that slide simply is that there is a large pool of, let's call them Lego blocks, and you can arrange these Lego blocks, these components, such that your experiment becomes feasible. Good. Now back to the competition. Here you see the pictures of all the previous winning teams. Well, actually, there are not the winning. Yes, there are the winning teams of this year. And well, we hope that we can also welcome you soon at CERN to be one of these winners. It's going in the wrong direction. And now, in order to inspire you, I quickly want to show 3 of the experiments that have won the Beamline for Schools competition in previous years. In 2015, we had a team from Italy. They were called Leo4G, and they asked a very simple question. They wanted to know if it was possible to detect particles with a webcam. You all know that the webcam can detect light, but can it detect particles too? You see here on the lower right-hand side of the picture the electronics that is inside of the webcam, and we've put it into the beam. And then we had to solve a number of problems, like will there be electronic noise? Is the beam going to destroy the webcam? Will the beam hit the webcam at all? And all of these problems have been solved by the students with help from us. And in the end, the team has seen tracks of particles in the image sensor of the webcam. That is the image in the center, the white line on the black background. That's a trajectory of a particle that was crossing the image sensor. So thanks to this experiment, we now know that a webcam or a camera in your smartphone is also a particle detector. In 2015, there was a winning team from Poland. They had heard that scientists were exploring the structure of the pyramid in Egypt using so-called muon radiography. Muons are particles that are moving at very high speeds, almost speed of light, and they can punch through many, many meters of stone. And there were scientists that have put detectors, muon detectors, into these pyramids to learn more about their structure, their architecture. And this team from Poland wanted to understand how muon radiography works. Therefore, we have shot muons through blocks of limestone. You can see them here in the center of the image. The problems that we had to solve was how to produce a muon beam, and then we had to measure the absorption. And by using the detectors that I've shown you before, we measured the muon absorption. And in the end, we have built sort of a small pyramid. You can see this 3x3 matrix in the lower center of the slide, where 3 of the 9 pyramid stones were missing. By using the data that the team had collected during the week, they were able to reconstruct the shape of this pyramid. Then in 2018, last year, we had a winning team from India, from Mumbai. They wanted to understand how relativistic particles, that means particles moving more or less at the speed of light, are deflected in a magnetic field. So we had to decide what particles we want to look at. Are we doing this experiment with muons? Are we doing it with protons? Then we had to see how can we measure the tracks of these particles with high accuracy. We had to understand the properties of the magnetic field. Well, again, here in the on the slide on the bottom right-hand side and in the center, you see the experimental setup. In sort of dark yellow, there is the magnet, and then these rectangular shaped objects with the color of copper, they are tracking detectors. And taking data in this setup, the team has been able to precisely measure the deflection of the muons and to reconstruct how these relativistic particles behave in a magnetic field. And actually recently they have written up their experiments in a scientific paper. Okay, so we are now at the end of the second question. And we are now taking your, at the end of the second session, and we are now taking your questions specifically on the Beamline for Schools competition.
And remember, if you have any questions, please put them into...
I can already see the first one. It says, can we change temperature inside the accelerator? Temperature here is not something that matters. What matters is the energy of the particles, and yes, this can be modified. Then, can a team use its own electric devices inside the accelerator at the position of the fixed target? Yes, this is possible. You can bring your own sensors. What about properties of particles? They are rough or approximated. No, but I can't say much about the proton spin.
No, this is also still ongoing research, actually.
Yeah. Then about baryons, no. At DESY, we only have electrons and positrons. But you have therefore both matter particles and antimatter, and there is a lot that you can do with electrons and positrons.
Sorry, sometimes we take a bit because the questions are jumping in our chat here up and down. It's not so easy to grab them.
Why can you not use biological material? Well, this is something that we are not doing also as professional scientists in the labs here. The point is that the particles can change the DNA of living material. Therefore, if you had an organism, this organism could have a mutation, and that is something that we don't want to have.
There are two very important questions. So one is about the BL4S FAQ, which is still concerning DESY and LNF. So LNF is another accelerator, a research lab in Italy. Unfortunately, there will be no winning team next year there because they had some technical issues and their schedule is a bit delayed. They might take part the year after, we will see, but next year, like this year, the winning teams will come to DESY, so you don't have to worry about who decides where to go. So this is actually fixed already with DESY again.
Where will you submit the video?
Yep.
The video and your written proposal has to be uploaded to the Beamline for Schools website. This is cern.ch/BL4S.
So during this week, the submission form will be open probably tomorrow and will be open until end of March. And in this submission form, you will upload a PDF file for your written proposal and a link to your video. You will have, but this will also be written there. You will have to upload your video on a video platform like Vimeo or something on YouTube.
Yeah. There is no age limit for the participation, but the winners have to be at least 16-year-old in October 2020.
In September.
September 2020. What if I know nothing about physics? Can I still take part in the competition? Of course. And once you've taken part in that competition, you will know a lot about physics. there are too many questions.
Yeah, I
can't
saw one
follow
quickly.
it.
What should be the format of the written proposal? It will be a PDF one. So you can write it however you want, but you will have to submit it in PDF format.
Do we register separately or just upload? You register as a team and you upload your proposal as a team.
And online is already a list of information you need to have available in order to fill out the submission form, because you will not just upload your proposal, you will also have to fill in some details about your team members and other things which we will ask.
Is it possible for Daisy to provide some relatively cheap and abundant material like ozone? That's no problem. We have a budget for materials, so we can buy whatever is needed to do your experiment if it's not too expensive.
Can a team run their experiment more than once?
As a winning team, you have access to the facility for one complete week. And in that week, you can do whatever is necessary to collect the data for your experiment.
No. Should the proposal be based only on the example experiments or on any other experiments? Everything is possible. The example experiments document we have online should be a document to inspire you if you have no other idea and you can work one of these out. But you can also submit any other idea you might have. So most of the proposals we get are actually own ideas from the teams.
And it doesn't matter whether you take one of the examples or your own creative idea. Your chances for winning the competition are equally good for both approaches.
So this doesn't really matter. It depends really how you work it out.
Yeah. Can we have a stationary target made out of baryons that can be targeted by electrons and protons? No, because baryons are not stable particles. Therefore, you cannot make a target from them. But there are many other things that you can do with electrons. You can, for example, shoot them at different materials and then find out how efficient these materials are to shield the electrons. That is something that is, for example, relevant for people that are building spacecraft to protect the astronauts and the electronics in the spacecraft from cosmic radiation.
A minute ago, I just saw a comment about the third part of the presentation. We might not get there. It's also not the most important one. It would have been about other educational offers, which you can also find on the CERN website, or you can ask or send us questions afterwards, and then we can answer this. I think Beamline for Schools is more important for now.
What are the products of a collision between two electrons and positrons? Well, usually you get more electrons and positrons, and you also get a lot of photons.
I'm sorry for interrupting, but
yeah, and this depends highly on the energy you collide them with, what you can get out.
What are your criteria to choose the winners of the competition, Sarah?
Very important question. So it's also on our website. It's written there. We have several criteria. So first of all, it's also creativity and motivation. So how creative are you, not only with your idea, but also, for example, with the video, which is also evaluated. How do you motivate your experiment? Is it, also how you write it? Do you follow the scientific method? So that means, do you really write what you want to do, why, how you want to do it, how you use the detectors, and what maybe even problems you might encounter and how you could solve them. So all these different things play a role, and of course the feasibility of the experiment as well. And in the end, we get these all together, these criteria, and choose the winning teams.
The next question is, what materials will be provided? Well, in short, we are providing all the materials that you need to do your experiment, unless they are extremely expensive. But you are, of course, also free to bring your own materials to the experiment. Well, we've already talked about the video submission. What will happen if the proton hits a person? Well, the person actually doesn't feel that. But protons are ionizing particles. That means that over the time, the persons can get cancer. And that is why in all the facilities where we have accelerated beams of particles, we have very high safety standards to make sure that there is absolutely no risk to anyone working in these areas.
One very quickly, I see that some have to leave because school is over. Yes, this video call is recorded and we will send the link later. Bye-bye. And so you can watch also the end.
And well, don't hesitate to contact us via our email address. We are going to answer all your questions in, well, as much detail as we can.
There's a question if you have to do some experiments before submitting the proposal. No, this is absolutely not necessary. You can, but you don't have to. I think most of the teams do not do this. They meet with some experts or teachers or mentors and just work on their experiments really and meet up in school or something, but you don't have to do experiments themselves beforehand. No.
Mm-hmm. How do we format the proposal? Well, as Sarah said, just send it to us as a PDF or a Word file.
No, only PDF.
Yeah.
And you can find examples how such a proposal looks like on our website, because all the 12 winning proposals we had so far are online on our website.
Can we write the proposal only for the electron-positron collider, or can we consider other facilities? In 2020, it's only the electron-positron collider.
Exactly.
Do electron-positrons require high-energy collisions? Well, this is something that you don't have to worry about. We are providing you with an electron or positron beam.
One question, can a 14-year student participate? In general, yes. As we said, there is no age limit. In case you will be winning the competition, we can only invite students who are at least 16 years old starting September next year. This is the only condition we have due to safety reasons.
Mm-hmm. Will we be able to use the DAISY beam dump? I don't think so.
No.
But you can direct the electron or positron beam at your own target and then study how the beam interacts with this target. This is pretty much what a beam dump is doing. Can we create potential difference in the collision chamber? I'm actually not sure I understand that question.
No, this is unfortunately not clear to us because we don't have really a collision chamber itself. It depends what you want to do with the beam, if you have collisions and where, so that depends highly on the experiment you propose.
If we are 15 plus with only a few months left to 16, yes, you're fine to go.
Yes. So really, once again, you have to be, in order to be invited, you have to be 16-year-old on the first day the program starts, which will be some point in September next year.
Mm-hmm. What do you plan to achieve by atom fission? Well, this is not anything that we are doing in Beamline for schools. And actually, fission and fusion here should not be confused. Mm-hmm. Fission is what you do in conventional nuclear power plants, and therefore, the aim of that is to produce energy. And atomic fusion, as it is happening in some research reactors at the moment, has the same aim to produce energy.
Mm-hmm. So if you have some suggestions for persons from India to help students, of course, first of all, on our website, we have national contacts in many countries, also in India. Have a look. There are 2 people from India helping you, but we have also many people we know now. For example, Sham, one of the team coaches from last year's winning team, is probably very happy to help you in whatever you need or to put you into contact with people who can help you. Okay. So just write us if you cannot find anyone.
If you are not 16 in next September, then we are sorry we cannot invite you to DAISY if you are a winner, but you can still enter the competition, you can still win one of the second prizes, you can still get a certificate from us.
Yes, and you can take part remotely from home. We had that as well already. Also, when teams were too big to invite them completely, that part of them we invited and the other part took part remotely. So this is possible.
Does TB23 exist at DAISY? I think this is a question about different beamlines at DAISY.
Yeah.
Well, that's not something that you have to worry about. We are
No.
going to find a good beamline for
We
you.
have one of the beamlines. You don't need to worry which one it is. The conditions are good for that, so don't worry about that.
Can we use the full beam energy directed at a target at very low temperatures? Well, technically yes, but we would then have to see how we cool the target.
And how low the temperatures have to be.
Yes.
So when the program will actually take place and when the winning teams will be invited highly depends on the accelerator schedule of DAISY. It will be most likely next year, end of September, beginning of October, around 2 weeks during that time. This is almost fixed.
I read the next question. What we meant is, are we confined to objects or can we also use electrical fields as variables? Well, you can, of course, also use an electric field. You can, for example, shoot an electron through a condensator. But well, then you would have to compute if the field strength has an effect on the particle. But technically, yes, this is possible.
There's another question with low temperatures.
Okay, there is another question about cooling. I'm not actually sure where the Curie point is. I think it depends on the material. Well, if we need cooling with liquid nitrogen, we would have to see with DAISY if that's possible, but I would not rule it out from the beginning.
So can we send the same proposal, not the same proposal, a proposal on the same theme of the previous participants? In general, yes. Of course, it should not be absolutely the same proposal. There have to be some differences, but the general theme can be the same if you work it out nicely with a few different aspects than before.
What is the minimum number of people who can participate?
So you should be a team of at least 5 students. So this is really teamwork here. You cannot do these kind of experiments alone, also in pure research as we do it here alone. So 5 students is really informative.
The winners are going to be at DAISY for roughly 2 weeks, maybe 12 or 13 days. There are some days reserved for a little bit of sightseeing in Hamburg, for safety training, for giving you some theoretical background. And then within this 13-day period, you will have 8 days at the accelerator itself.
So far it has always been 12 to 13 days. We invite the teams.
Can we consider in the magnetic field and what power? Yes, we have 2 different large magnets with a field strength up to 1.25 Tesla.
So the question, do we need a clear hypothesis? And if so, would it require rigorous mathematical justification? No, it does not. So you don't need to have every single detail or calculate everything yourself. That is not what we want. We want you to have an idea and to really let us know what you want to do, how you want to do it roughly, but you don't need a full detailed proposal. We can still work on the details together then in order to implement them. Sorry, the questions are jumping again. Just a second.
No, that's me scrolling. The last question was, may I know the topics? What topics are you referring to? No, there is no particular format. Anything that fits into a PDF is fine. Would it be possible to have a single isolated proton as the target of the beam? I don't think so. protons are very, very small, and I wouldn't know how to position that proton into the beam. So you have to use a more massive target, which therefore consists of many, many protons.
Yeah, and even if you could isolate a single proton, you probably wouldn't even hit it with the beam.
Well, the next question is not about BL4S. What are your criteria of hiring your employees? If you want to be an employee of CERN, you have to be a national of one of the CERN member states. And well, beyond that, it's about your skills as an engineer or scientist.
Any books we can refer to? There are so many. So one thing we want to do in the future is to put some resources, some links online. It's not there yet, but if you have some specific question, you can write them to our national contacts or to our BL4S team ourselves, and we can see how to help you. So at the moment, there are so many books and resources online. Just have a look what you want to know. I'm sure you will find something.
Yeah. Well, we had mentioned one book, that's the famous God particle of Leon Lederman. I've read it myself. It's a very nice summary of particle physics up to the 1990s. Do equations count towards our 1,000 word limit?
No, there is also now written a bit online, so not everything counts. You have acknowledgements, you have maybe some words in figures or something. So this you don't all need to count. So if you have a reasonable amount of words in these things and also equations, no, they don't count. If it's 1,050 words, it's also not such a big problem, but just respect roughly this length.
So the next one is about our criteria for selecting the winners. Well, as Sarah already tried to explain to you, we are looking at a number of different qualities. There is one criteria that is non-negotiable. If you want to be a winner of the competition, your experiment has to be feasible within the technical conditions. And you should also not make too many big mistakes in the physics. But we are understanding that you're high school students. We understand that you are not experts in particle physics. So if we feel in your paper that you are motivated, that you have made a bit of an effort to understand your experimental proposal, then I think you're already fulfilling all of our criteria.
Exactly. If you have a look on the proposals we have online, you will see that you don't have to have them in detail with all mathematics in there. That is absolutely not necessary. So another question, will certificates be issued for all participants? Yes. So far we have printed them out and sent them all over the world. That gave us some issues. So from next year on there will be only digital certificates, but this is much better anyway, as many of you would like to have them for applications or something. So yes, every single participant will get a certificate with his or her name on. That's why we are asking also a lot of questions in the submission form in order to get all this right.
Mm-hmm. There is a question about the target that consists mainly of protons. Well, that's difficult. As soon as you use anything else but hydrogen, you also have neutrons, and the electrons cannot be avoided anyway. But I think you have a particular experiment in mind. It's maybe better if you contact us about your ideas, and we can then give you some more targeted answer. Has a member of our staff had any side effects because of an experiment? Yes, we all get much too little sleep when we are doing experiments. But in terms of health consequences, I would say no, this is not a
It
problem.
is very safe, and we have a lot of safety regulations in place. That's, for example, also why we can only invite students being at least 16 years old, so it's quite safe.
Yeah. In TB1, does a team have to choose between an electron-positron beam? Yes, you can make that choice. We can deliver you either electrons or positrons.
But you can use both during your experimental time, so it's possible. Not at the same time, but during your stay at DESY, you can use them and can switch, for example, from one day to the other, or even during one day.
In 2013, LHC identified the discovery of Higgs boson. In addition, there are many achievements. So to what extent will the successful application of these discoveries lead the advancement of our technology? Ask me again in 50 years. If you look at all the high-tech gadgets that we have at the moment, like video conferencing facilities, lasers, smartphones, satellites, whatever, all of these technologies are based on the foundations in physics that have been laid in the first half of the 20th century. The delay between fundamental science and technical applications in this field is about 2 to 3 generations. Therefore, at the moment, it's completely unclear what the foundations that we are laying at the moment will enable in terms of technology in 2 or 3 generations.
Quickly, what we scientists eat, the same as everyone else in the world, more or less. Probably sometimes not enough because we are so busy with science. Can you help us with the beginning? Where is it again? In the engagement with pupils and the schools, for instance, with some previous videos. So we have a lot of information, documents, links, whatever on our website. So this is the first thing, also some promotion material as well, which you can use. Furthermore, we have our team and the national contacts who can help you answering a lot of questions. This is always possible. And if you have specific questions or would like to get into contact with a special previous winning team, for example, I'm pretty sure they are happy to answer any questions you might have about their experiments as well.
The maximum number of participants in a team, well, there is no maximum, but in case your team wins, we are going to invite at most 9 students.
Plus 2 team coaches.
Is it possible to organize experiments including the interaction with matter with laser impulses pump probe? So interaction with matter, yes. Interaction with lasers, I'm not sure. I would have to look at it. And I don't know what a pump probe is.
So, will chaperones and parents be included in the team that escorts the winning students? Mostly the answer is no. So for one winning team, we invite up to 9 students and 2 team coaches, as said already. The 2 team coaches do not have to be teachers. For example, we also had a professor here, or it can also be a parent if the school agrees to send this one as a team coach, but we cannot invite otherwise all the parents. This is unfortunately not possible.
I just joined now the call. May I know what Beamline for Schools is in short? Beamline for Schools is a science competition that CERN and DAISY, 2 large physics laboratories, are organizing. We are inviting high school students to propose a particle physics experiment to us, and we are inviting some of these students to do their experiments at the laboratory in Hamburg at DAISY.
Next question, if our team wins and we get to try our experiment, will CERN scientists help us about our experiment? No, you will do it completely alone? No, that was a joke. Of course we will help you. So CERN and DAISY scientists together, we as a team, of course we will help you. We will introduce you to everything so far that you can partially do it alone, but you will never be completely alone. You will always do it together with our team.
How many particles did we discover during our experiment this year? Well, we have seen some new bound states of quarks. Well, I don't want to confuse you with the names. They're called petaquarks and pentaquarks. So maybe we have seen 2 or 3 new particles this year.
Okay, the scientists' marriage choices, I think we skip that. I cannot really tell. I guess it's as normal or confusing as everywhere else.
Can we do experiments to combine and check the energy emission of 2 different particles? Well, this is also something that we would have to look at in detail.
Yeah. So I see the last comment that more schools are going to be closed. Of course, for you it's much later than for us. So anyone who has to disconnect now, thanks for connecting and hope to see your proposal or maybe questions before soon.
Yes. There's a question about black holes. Well, short answer, don't be afraid of them.
No. No.
Sorry, I can't use the chat.
Yes, okay.
Okay. Then quickly your question.
Okay. I can, or my team, in the case of winning this, we can repeat the experiment on DESI more than one time.
Yes, you have 8 days. You can do your experiment as often as required within these 8 days.
Oh, thanks.
Exactly. It's not that you have only 1 hour, you do it once. You will also change some parameters, maybe like the energy, or use different particles, or have other material, whatever you're doing. So yes, it takes time. You always need some statistics, so it's not done in one day.
So can I ask my question?
Go ahead.
Okay.
So if we are less than 16, then how will we perform the experiment?
Yeah, we just see the question in the chat as well. So, well, first of all, if you are now below 16, it's not a problem as long as you are 16 next September on, from next September on. If you're still below 16 years old, well, don't worry too much now. Just take part. If you should really win the competition, then we can only invite those ones of your team who are at least 16 years old, and the other ones can, as I said before, take part remotely. That means via video conferences, sharing the data, chatting with the team, and you can still take part in the analysis and everything else. We can just not invite you directly to DESI, but you still take part.
What level of mathematics do you expect us to have in our submission paper? Well, that depends, of course, a bit on what you're proposing, but I would say normal high school level of math is enough. If you have well, equations to illustrate the physics, you can, of course, copy them into your proposal. What is important is that whatever you write into your proposal, you have to understand. So don't impress us with formulas, but don't worry about the mathematics.
Yes, and have a look again on the proposals we have online. You will see some with a lot of mathematics and some with almost no mathematics, so everything is possible. So the question again with the with the age. So no, we cannot round up due to strict safety regulations in all the research labs. You have to be again 16 years old on the first day of the program. Even if your birthday is 1 day later, we unfortunately cannot invite you. Sorry.
Yeah. What about studying how feasible it is for a black hole to hit us within a relatively short amount of human time? Well, as said before, this probability is, well, for all we know, 0.
Yeah. Once again, since the age issue is here up to date, if you are so young, see it positively. You can take part another time, and then we can invite you.
Yes. Are there magnetrons in your lab? I'm not sure. This is something that I have to check.
Yes. So we might not know everything. If there are questions we cannot answer, send them to us, and we'll take care that we get the answer. What? How old we are?
Oh my God, that's older than time.
Old enough. Well, above 16 years, definitely.
Yes.
Okay, we might have not answered all the questions which are in the chat, which were really many, but I hope that we answered most of them. Is there any other urgent question you have? I mean, after the call, we are still available and you can write us via mail. So if you have more questions in the future, no problem. Oh, there is something else. So other resources other than the CERN website?
Well, I think there is actually a lot of good content on Wikipedia about particle physics. Some of it goes into the deep mathematical details, but you can get a nice overview of the concepts on Wikipedia.
I mean, nowadays it's better than it has been in the past, really much better. You can find so much. Even there are so many nice videos on video platforms explaining physics or anything related to it, also showing simulations in order to explain how some things work. You can find so much. I would just say Google and you will find more than you can watch in the next month.
But there is an important question. What is the mail ID to contact you in future? Let me quickly share my screen again. So here you see our logo. It says Beamline for Schools. And below the logo, you see our website, cern.ch/BL4S. That's all you need to know. If you go onto that website, you find all the documentation and you also find the email link to contact us.
Yes, this will not change. So just remember that everything else you will find there.
Stop sharing, otherwise I can't see the chat.
Exactly. Okay, this one we do not really understand regarding the proposal. Does it have to be right for us to be winning? We are not sure what you mean by right for you.
Well, the experiment has to be feasible. But if you make some mistakes, well, don't worry.
So we were asked concerning our mail address, which is also on the website. So this is our official Beamline for Schools mail address, so our whole team will receive the questions then. No, you still do not have to worry about the beamlines which are in the sketch of Daisy. There are several beamlines available. We have reserved one. You do not have to worry about which one it is. Everything you need to know about the beamline is in our technical document. That's all you need to know. Is there anything else you want to urgently know?
Okay, understood.
Yeah, well, it seems that we are finally coming to the bottom of all of your questions. It has been a very intense 90-minute session. I think it's now, time to wrap up. We thank you very, very much for your interest. Please do contact us. We are happy to answer your questions on a more technical basis. And of course, we are all looking forward to meeting you as participants and maybe even as winners of this competition.
Yeah, and also if you are below 16, because I see it again, take part. It's worth it. So don't worry too much about it right now. Just take part.
Okay.
Okay, so then thank you all very much for connecting to all over the world, and hopefully we will hear back from you with questions and of course your proposal until end of March.
Yeah. Well, also a big thank you to TEDAT, represented by Bobby, for organizing this event.
No worries. Thank you all at CERN. Thank you, Marcus. Thank you so much.
Okay.
Bye-bye.
Bye-bye. Bye, everyone.
Bye.
Bye. Thanks. Yeah.
Goodbye. Goodbye.
Bye-bye.
Goodbye, everyone. Goodbye. Goodbye, everyone. We will see you.
Jenna? No, I didn't see her.
Goodbye. We will never see you again. We'll see you again.
Bye.
Bye, Sana.
Bye. Thank you. Thank you.
Thank you.
Did Paul start his courses for VP?
I guess he did, yeah.
He did, yeah. Was he the same as you guys?
Hey,
Hey, Will.
you all right?
Yeah. Yes, yes, yes. Here, let me actually stop recording.